Hello, I hope you are doing well. I am doing great. Thanks for asking. In this video, we are going to be tackling this beginner problem. So I am learning C. I guess I am beginner. I am a beginner at that. And I have three solutions for this. So we are going to start with the brute force solution. We are going to make it a bit more efficient. And then finally, we'll find a way more efficient solution for it. So the problem is to find the sum of all multiples of 3 or 5 below 1,000. So we need to note two things. One is we are looking for multiples of either 3 or 5, right? Not 3 and 5. So the question you're going to be asking is, for example, when given 9, is 9 divisible by 3? And you're like, yes. So we don't need to check whether it's divisible by 5. Then another one is 10. We do, is 10 divisible by 3? No. Then we ask ourselves, but is it divisible by 5? We are like, yes. So that's also a tick. And since C's OR operator short circuits by default, well, that's going to work out pretty nicely for us. Then another example is for 15. We only check is 15 divisible by 3, and you're like, yes, so you don't need to check for 5. Then for a number like 7, obviously we are going to end up checking for both, and then it's still going to be a no. So for the numbers like 7, which are not divisible by either of them, we have to check for both. You get the whole point of this. And then the other thing we need to note is that we are looking for numbers below 1,000, not up to 1,000. So that means you are going to go from 1 all the way to 999. And I just noted this to myself so that I avoid those off by one errors. So the first implementation is the brute force implementation. And we are going to walk through every single integer from 1 to 999, checking for the divisibility. And if a number is divisible, we are going to add to our total. So this is like a simple demonstration of what's going to be happening. So here I have just from 1 to 100, and then, multiples of 3, multiples of 5, but doesn't matter. I'll be looping through every single one of them. Yeah, so let's start with the brute force implementation. So I am here in the terminal. So let's start with main.c. I am going to include the stdio, probably going to have a lot of printfs. So let's define main, which is going to return an int. Main doesn't take any argument, so we have void there. And then let's have main return 0. And obviously, where else would we start if not with a hello world? So let's compile and run that, and we have our hello world. So for the brute force implementation, let's call the function, we're going to call the function sum multiples. Sum multiples, it's going to be a long one, sum multiples of 3 or 5. And this function, it's going to return, let's have it return an unsigned int, and then it's going to take another unsigned int. I want you to take another unsigned int, and we are going to call it the limit, which is 1,000 in this case, right? So what do we want? We want to initialize a total, so another unsigned int total, and you're going to have it start at 0, and then for unsigned int there are a lot of them. So for unsigned int index, and let's start at 1 actually instead of 0, and we are only checking, is this index strictly less than the limit? And then we are going to increment the index by 1. Then we now have to check for the divisibility. So we have to say if, so to check for the divisibility, we are going to use the modulo operator. So to know if a number is divisible by 3, for example, we'll check the index and then modulo 3, is it equals to 0? Since modulo checks for the remainder, if index divided by 3 has no remainder, it means that it's divisible by 3. So if it's divisible by 3, or the index is divisible by 5, what I want you to do is take the total, and you're saying the total will be the total plus that index. And then at the end of the day, return me the total. Then let's try running this. Let's first do for the first 10 values. So printf sum of multiples of 3 or 5 below 10 is equals to, let's have a %u since it's an unsigned int, and then call the function. So some multiples of 3 or 5, and the limit is 10. Okay, there we go. So let's compile and run this. So this is giving us 23. So let's see, we have 3. So we're talking about 3 plus 5 plus 6 plus 9, right? So if you take 9 plus 6, that's 15, and then 15 plus 5, that's 20, and then 20 plus 3, yeah, that's 23. So let's try for 20. So sum of multiples of 3 or 5 below 20% u, some multiples of 3 or 5, and then let's have 20. Okay, so make run, and this is giving us 78. Let's just confirm that. So after 9 we have 12, we have 15, and then we have 18, right? Yeah, the 20 is not included. So when you take 18 plus 15, that's going to be 33. 33 plus 12 will be 45. 45 plus 9. Actually, I forgot 10. Yeah, I forgot 10. After 9, we are supposed to have 10 since we're checking for multiples of either 3 or 5. Okay, let's start again. So this is 18. 18 plus 15, that's 33. 33 plus 12, that's going to be 45. 45 plus 10 will be 55. 55 plus 9 will be 64. 64 plus 6 will be 70. 70 plus 5, 75 plus 3, 78. Okay, our solution is working. So that is the brute force implementation of the problem. So I guess we are ready to make it a bit more optimized. So here comes our second implementation. And for the second implementation, do we really have to check each single number? Remember, for example, in this case, we are checking each single one of these. One, we know that one isn't divisible by any of them. It's in fact less than both of them. So we don't have to check for one, neither do we have to check for two, neither do we have to check for 4. So what can we do? We can, for example, when you look at the multiples of 3, we know that we need to start at 3, and then from there, we'll be making jumps of 3. So we start at 3, plus 3 we get 6, plus 3 we get 9, plus 3 we get 12, and so on. So long as we are strictly below 1,000. So that's the whole explanation for this, and we'll still have to do the same for 5, of course. So here I have a little demo of what will happen. So when you look at this keenly, both of the balls are going to land at 15, and then they'll land at 30. So if we start counting, no, not counting, if we start adding the multiples of 3, we will add this 15, and then for the multiples of 5, we will add the 15 again. So that's going to be a bit of a problem because 15 is supposed to be counted only once, not twice. So basically, this is like an illustration of that. When going through the multiples of 3, we include multiples of 15, and when going through multiples of 5, we include multiples of 15 too. So 15 is included twice, basically. And Just something to note is that 15 is included twice because it is the LCM of 3 and 15. Both are divisible by that. So we basically just need, after all this, we need to remove all the multiples of 15. So basically that. And what you're going to do is we take the multiples of 3 plus the multiples of 5 and then minus the multiples of 15. Yeah, that's the whole explanation. So let's get to it. So for a second one, let's just remove everything here. And then we are going to initialize 3 totals. So I'm going to say unsigned int. Let's just go with the total for 3's. Then unsigned int, we are going to have another total for 5's. And then finally, another unsigned int for the totals of 15. And we are initializing all those to zeros. So let's start with the 3's. What do you want to happen? So we are going to say, if I can get that right. So for unsigned int, I'm I'm still going to use index, but this time I want you to start at 3. And what am I checking? I need to ensure that that index is strictly less than the limit, right? And then after that, then I'll be incrementing this index by the 3. So I'll say the index will be the index plus 3. And then since this time I'm strictly looping through the multiples of 3, I don't need any check inside of that. So I'll just say take the total of 3 and it's going to be whatever total is there plus the index. Then you're going to do the same for 5. So for unsigned int index equals to 5. So again, you see, we start at 5, then we ensure that we are strictly less than the limit. Then we'll be incrementing this by 5. And the total for 5 will be the total for 5 plus the index. And of course, we're going to do the same for the 15. 15 index strictly less than the limit, then this time we're incrementing by 15, and then the total for 15 will be total for 15 plus the index. And what do you want to return? We want to return the total for 3's plus the total for 5's minus the total for 15. And that's it. So if we run this, it should still give us the same answer. So we're going to compile and run that, and there we go. So our second implementation is working. So at least we have optimized the brute force implementation a bit. We are doing way less iterations now, but the question is, can we do better, right? So let's look at the third and final implementation. And in this case, we are going to consider the arithmetic series, because what are we actually computing, right? Let's take a look for the 3. We are taking 3 plus 6 plus 9 plus 12 all the way to 999. That is the series, right? What if we factor out the 3 from this from the series? If we factor out the 3, we are going to have 3 times, then we have this other series of 1 plus 2 plus 3 plus 4 all the way to 333. But does this look familiar? Yeah, this is like the sum of the first n integers, right? We have seen that before somewhere in a math class somewhere. Or if you haven't seen this yet, I have a small demo of how to go about it. So actually, let's just let's just get to it. So let's start with how do you get the sum of the first 10 integers? I have them here. What you're going to do is we're going to add them from the outside coming to the inside. So we take 10 and 1. When you add those, you get 11, right? When you take 2 and 9, you get another 11. When you take 3 and 8, 11, 4 and 7, 5 and 6. So what do you notice here? When you add the corresponding outer terms, you're always going to get the same middle term. Like, oh, no, not the same middle term. You're always going to get the same value. And the thing here we need to notice is the 11s, we have 5 11s. So the question is there a relationship between our n, which was 10 in this case, and the number of pairs? Yes, because we got 5 pairs. So to get the 5 has to be half of 10, right? So that's like doing n over 2. And then when you take at this, the summation, 11, is there a relationship between the 10 and 11? Yes, that's just 10 plus 1. So it turns out that this formula generalizes to this. So actually, let me move myself over a bit so that you see that. So we have said we take n over 2 pairs, 10 over 2, which is 5, multiplied by n plus 1, which is 10 plus 1. And this formula is going to generalize for any value of n. So to get the sum of the first n integers, all you have to do is n times n plus 1 over 2. So that's that. Let me bring myself down again. There we go. So if we plug this back into the formula, remember what we had. Let me go back here. So we had factored out the 3. Now let's plug this back in. When you plug it in, we are going to say it's like taking 3 and then multiplying it by this formula of n times n plus 1 all over 2. But 3 isn't really special in this case. That can be 3, 5, whatever number we decide to find the multiples of. So this is if we replace it by an x, an arbitrary variable. That's going to be x and then times that formula. So the only thing in our case is how do we find the number of terms? Because this formula relies on the number of, or on me knowing the number of terms beforehand. So the question is how many multiples of x live below the limit? Remember in our function, we have the limit argument, right? And so we need to find how many multiples of x, in this case 3, 5, live below that limit. And it's pretty easy. For example, if we let's take for 5, right? In the case of 999, if we take 9, no, actually the limit was 1,000. So if we take 1,000 minus 1, that gives us 999. Divide it by 5. It's going to give you probably around, I think, 195. So it's going to give us 195 point something. So that is where integer division comes in, because this 195 is the number of terms of the series of 5s, right? And the same for 3. If you take 999 divided by 3, you're going to get 333, which is the number of terms for the series of 3. So we are going to be doing integer division for that, since we don't want the we don't want the values after the decimal points. We're only interested in like the integer part. So that's basically how this is going to go. Yeah. And then it's the same thing. We are going to find the sum of the multiples for 3. We find the sum of the multiples for 5. And then we are going to subtract the sum of the multiples for 15. Yep. So that's it. Let's implement it. And I'm actually thinking, let's just have another function, unsigned int, and we're just going to call it sum multiples. It's going to take 2 arguments. So let's have it take an unsigned int x and another, oh god, if I can just spell this right, another unsigned int limit. And so what do we want to do? The first thing we have said, we need to calculate the value of n, the number of terms. So you're going to say unsigned, oh god, unsigned int, I'm just going to call it n. And so we have said this is going to be, we take the limit, we minus 1, and then we divide it by the value of x. So now that we have the value of n, we can calculate our formula. So we are just going to return, let me wrap this. So it's going to be something divided by 2. And what is that something? So we are taking x times n plus 1, and then all of that divided by 2. And that's literally it. Did I get it right? Let me confirm. Yeah, x times n plus 1, and all of that divided by 2. The reason why I have the divided by 2 on the outside is to avoid integer division prematurely. For one, I know that this expression in these brackets, it's going to produce an even number. So yeah, so when it produces an even number, there can't be integer division in this case. So we have that. Now it's time to call that function down here. So we are going to replace all this with some multiples, and then we are going to provide the x. Let's start with 3, and then we drop the limit there, then plus some multiples, 5. Again, we drop the limit there, and we are going to subtract some multiples. This time we're doing for 15, and then again we drop the limit there, and actually this is what we want to return. Yep, yeah, that looks about right. Let's run, and there we go. So we got it. And actually I just remembered we were supposed to do this for 1,000, right? Not 10, 20. So we are going to replace this with 1,000, then come here and do this for 1,000, and all of them should just give me the same answer basically. So yeah, 233,168 looks about right to me. So that was the formula implementation, which is obviously the most efficient. And actually, I think I had a comparison here. Let's take a look at the comparison. Where are you? So for comparison, the brute force, we are going to do 999 iterations and even more checks, I think. But assuming the maximum number of checks you're going to do is just the 999. And then for when just walking through the multiples, we'll have reduced the number of hops or the number of iterations by like 400. So when walking through the multiples, we'll be doing only 598, which is still pretty high for this question. But when using the arithmetic series, we are only calculating 3 instantaneous formulas. Now, I don't know much about big O notation, but I know an O of 1 when I see it. So yeah, that's it. Yeah, it was a good learning experience for me. Yeah, and I am hoping that you have learned something too. So as usual, thanks for watching and have a great day.